Hello and welcome to Count Her Math. Now that I officially have my college algebra textbook, we're going to start diving into the content. I'm not sure what format of video is going to be most helpful for students, so I'm going to try some different styles out these first few chapters. Please let me know in the comments if the video is helpful or what I could do differently to be more helpful for you. So our first chapter of this text is Chapter R for Chapter Review. This chapter is often covered very quickly in the college courses since it's assumed to be mostly review material. But not everyone enrolled in this course will have the same educational background, so to some this content may be boring while others it is brand new. This video will cover content in R.1 Sets. A set is a collection of objects. In algebra, these objects are typically numbers, but they could be anything, and each object within a set is called an element. In this set, each number is an element of the set. I could also name the set by using a capital letter. By doing this, I don't have to constantly write out the whole set whenever I want to reference it. So at the start of a problem, or wherever the set is first introduced, I would say capital A is equal to the set, or whatever letter I'm using. And then from here on, I can just refer to set A instead of writing out the entire set. We can also refer to sets in what is called set builder notation. This is more like a mathematical sentence that describes a set. If I was to describe set A in casual language, I would say something like, this set is counting numbers from 1 to 4. Set builder notation is a more formal and exact way of describing a set. So in set builder notation, this set would be written like this. When we read this, we would say, the set of all elements x such that x is a natural number between 2 and 7. When I read this statement, my brain interprets it more along that this set refers to elements or numbers as x, and x is a counting number between 2 and 7, so therefore the elements are the numbers 3, 4, 5, 6. The sets we've seen so far have all had a very specific number of elements, or we could say they are finite sets. We can also have a set that goes on forever. We would say that this is an infinite set. And we show infinite sets by using ellipses to say that this pattern continues. If we have an ellipsis that ends the set, then that set is infinite. But it is possible to have an infinite set while still having an ending value. For example, the set of all elements x such that x is a fraction between 1 and 2, because there are infinitely many fractions between these two values. We also have some different symbols that we use when we're talking about sets. Now that we have those up along the top, let's start going through these. The first symbol is used to reference the elements within a set. An example of this would be saying 3 is an element of this set, or 7 is not an element of this set. Now let's look at that capital letter U. The U is representing our universal set. When working with multiple sets at a time, to compare or contrast them, we will have what's called a universal set, which references every element among all of the sets. We can show this with a little Venn diagram. The entire box is your universal set, and then inside you'll have multiple sets. We could also have an empty set or a set with no elements in it. We call this a null set, and it can be shown with the double curly brackets or with a slashed O. An analogy we could use to describe this, the universal set would be a building that contains everything, and each room within the building is a set. A null set would be an empty room within the building. The names of the sets would be the room numbers, or in our case, the room letters, but the analogy does start to break when we try and put infinite sets into a room, but the general idea still holds. The next two symbols refer to subsets. If we have both set A and set B, and every element in set A is also within set B, then set A is a subset of set B. If this wasn't true, we would put that slash symbol to say it's not a subset. The null set has a pretty cool property where it is actually the subset of every set. Since a subset doesn't have to have all of the elements, it just can't have any extra elements. A null having no elements fits the rules of subsets. Next we'll talk about complements of sets. To have a complement, we first need to have a universal set and some original set within that universal. A complement contains all the elements that are not part of the original set. And we can indicate that a set is a complement with a little asterisk, and we read it as A prime. In set builder notation, a complement looks like this. And this would read, A prime is a set of all elements X such that X is an element of the universal and X is not a member of set A. The comma in set builder notation implies an AND statement. And the AND statement means that both statements must be true at the same time for it to be part of the set. We're also going to need to be able to find and label intersections and unions of sets. Let's continue using a generic set A and set B to explain this concept. The intersection between two sets is a set of the overlap between the two. So the intersection between set A and set B is a set of the elements that are in both A and B. Again, the word AND implies that both statements have to be true. We indicate intersections using this upside down U. And our set builder notation of an intersection would look like this. And a union between sets is the set that contains all elements from set A or set B. The only difference between an intersection and a union's set building notation is the AND versus the OR. So a union contains elements from one or the other, so only one statement has to be true at a time. They can have some overlap, but it's not necessary. Let's look at a quick example of each of these. If we have set A as 1, 2, 3, 7, 8, 9, and set B as 3, 6, 9, then the intersection between set A and set B are the numbers that are in common with both of them. In this case, those numbers are 3 and 9. And the union between the two sets would be all of the elements in set A, as well as all the elements in set B. If there's any overlap, we're only going to write the element once, even if it's in both sets. So in this case, the union between set A and set B is 1, 2, 3, 6, 7, 8, 9. The order that we write our set in does not matter. It can be written 1, 2, 3, 7, 8, 9, 6, which is just rewriting A and adding anything from B onto it. I prefer to write them in numerical order just to keep it clear, but whatever works better for you is the better way to do it. That is the end of R.1's text, but let's do some exercises from the book for some practice. I did mention in a previous video that I'm only going to do odd number exercises since you can already get the answers from the back of the textbook. But if I really like one of the even problems, I'm probably going to come up with a similar problem to go over it without doing the actual problem. So this is the list of the problems we're going to go through this video. Starting with problem number 7, use set notation and write the elements belonging to the set of all elements X such that X is a natural number less than 6. So our first thing is we need to discuss natural numbers, which I didn't discuss before. Natural numbers, or counting numbers, are one and the same, and they're the numbers 1, 2, 3, 4, etc. The important part is that it does not include 0. Natural numbers start at 1 and go up from there. So if we need to make a set of natural numbers less than 6, we can either start at 6 and go down, or we can start at 1 and go up. I like going from small to big, so we're going to start at 1. Now let's reread this question real quick and make sure that we're doing this right. Numbers that are less than 6. Well, 6 is not less than 6 since 6 is 6. So we do not include 6 within the set. The set is the numbers 1, 2, 3, 4, and 5. Questions 11 and 17 follow the same instructions, is asking us to identify each set as finite or infinite, and then determine whether 10 is an element of that set. And in question 11, our set is 4, 5, 6, continue that pattern up to 15. And we need to ask ourselves, is this an infinite set or is this a finite set? And the answer is that this set has an end. It does not end in an ellipse, and it doesn't have fractions or anything, so this is a nice finite set. Then we need to determine whether 10 is an element of this set. Well, if I'm doing natural numbers from 4 to 15, at some point I have to cross through 10. So for number 11, we have a finite set that does include 10. Question 17, a set of all elements x such that x is a fraction between 1 and 2. We discussed this exact problem back when we first discussed finite versus infinite, but let's discuss it one more time because this is a very important concept to understand. If I'm looking at a spot on a number line between 1 and 2, and it wants to know how many fractions are between 1 and 2. Is there an actual amount or is it infinite? I can put a mark at 1/2, at 1/4, at 1/8, at 1/16, and I can keep making that denominator change to be bigger and bigger, and as a result make the fraction even smaller and smaller, and there's no limit to how much I can do that. I can always make a bigger number on the bottom, or just change up the fraction entirely as many times as I want to. There is no end to the fractions. So we would say that this is an infinite set because there's no way for me to mark or write down every single fraction between 1 and 2. Then we have to determine whether 10 is an element of this set. Well, our set only goes from 1 to 2 at the very maximum, so it will never reach 10. So we would say 10 is not an element of the set. Alright, we're jumping ahead a bit to question 25, and the instructions tell us to use set notation and list all of the elements of each set. So we're given it in the sentence form and we need to turn it into the long form. So first we're going to read that we have a set of all elements x such that x is a natural number greater than 8 and less than 15. So our first step is to put a curly bracket. Natural numbers, so our counting numbers 1, 2, 3, 4, etc., that are greater than 8. So the first natural number bigger than 8 is 9, since 8 is not bigger than 8. So we're going to start at 9. And less than 15. 10 is less, 11, 12, 13, 14, and 15 is not less than 15, so that is the end of our set. Our next question is question 29, and it says fill in the blank with is an element of or is not an element of symbol. We have 5 blank, set 4, 6, 8, 10. Is 5 an element of or is 5 not an element of this set? There is no 5 in 4, 6, 8, 10, so 5 is not an element of the set. Question 49 is true or false. The set of all elements x such that x is a natural number less than 3 is equal to the set 1, 2. Is this true or is this false? Natural numbers start at 1 and they go 1 at a time, so 1, 2, 3. And it needs to be less than 3. 3 is not less, so we're just doing the first number in the natural numbers, which is 1, and then 2, and then we're done. So this is very much a true statement. Then we have another true and false question. Is the union between sets 1, 2, 7 and 1, 5, 9 equal to the set 1? Now this one's trying to trick us, but we're not going to let it. So if we see that we have sets 1, 2, 7, 1, 5, 9, well, the two things that are in common is a 1. 1 is in common with both sets. However, the problem's not asking us what's in common, because that would be the intersection. The intersection between these two sets is 1. However, it's asking us the union, because this is false, because the union should be, let's write down what the correct answer is. The union would be 1, 2, 7 from the first set. The second set already has a 1. Then we need to add 5 and 9. So if we wanted this to be a true statement, we would say the union between 1, 2, 7 and 1, 5, 9 is 1, 2, 7, 5, 9. Some more true and false questions. True or false? The intersection between 3, 5, 9, and 10 and the null set is equal to 3, 5, 9, and 10. Again, it's trying to trick us, but we're not gonna let it. Let's call this set A, and we'll call the null set null. So is 3 in both set A and in set null? There is nothing in set null, so 3 is not part of the intersection. In the same idea, 5, 9, and 10 are also not in the null set. So there is no intersection. The intersection between set A and the null set is the null set. So if we wanted this to be a true statement, we would say the intersection between A and null is equal to null. It is not equal to the first set. So this guy is true. This guy is false. What we could do, as another way to make this a true statement, is just flip the intersection symbol and make it a union. Because the union between set A and the null is set A. So if we change the question around and said union instead of intersection, it would have been true. It really wants to make sure that we know the difference between an intersection and a union. And we have one last question, again checking on that intersection versus union terminology. Question 77 is saying that the union between 1, 2, 4 and 1, 2, 4 is 1, 2, 4. And union means that we are taking everything from the first one and adding anything we missed from the second one to make a full collection of all elements that were between the two. In this case, 1, 2, 4 is everything. So 1, 2, 4 is the union. This one is true. What's really cool about this one is that it's also the intersection. We could say the same exact problem, but say the intersection instead of the union, and it would still be true. This is also a subset, would also be true, because the subset of itself is a subset. So when we have two of the exact same sets, it is a union, it is an intersection, and it is a subset. All of the above are true when it is the same set matched against each other. Thank you so much for watching, and I hope this helped. Like, share, and subscribe to follow along with the rest of the series, as well as all the other content I've made.